Okay, so we've talked about what makes an acid and a base a base. We've talked about some of the common properties. Next, we're going to talk about what happens when you put that acid in water, and then how you can tell the difference between strong versus weak. To start this, we get to talk specifically about things that can act as both an acid and a base. That's something that's called amphoteric. Be familiar with that word, amphoteric. It's kind of like an amphibian. It can do both things. It can be in land and in water. Amphoteric means that we have something that can be an acid or that it could be a base. The example that we like to use a lot is water. And so I have an equation down at the bottom. So it shows how water, let's see if I can write on here, water, there we go. Whenever you put it in water, now here's the double arrow. Now really this double arrow should look a little more like this, but sometimes PowerPoint it's hard to figure out the correct fonts. So water can dissociate or break apart when you put it, well, I guess not necessarily in water, it just breaks apart. It can form the H plus ion and the OH ion. That OH is called hydroxide. Now this H plus, it doesn't actually like to exist by itself. So it's immediately going to go find another water molecule and form this thing that's called hydronium. So down the bottom, we're just showing a little bit more, we could say proper reaction, showing that two waters, one of which is going to break apart and form that H plus and OH minus. The H plus reacts with water to form hydronium. So water can split apart. Well, let's see what that means or how much this is actually going to happen on a regular basis. So this one is just showing the Lewis structures of what's happening whenever that amphoteric water will break apart. So we start here with water. There's our H2O. We have our double arrow. The double arrow refers to the fact that this is a reversible reaction. We're going to make some of the product. Some of the products are going to come back and make some of the reactant. Now water, remember, can split and form a proton, H plus, and hydroxide. There's our special hydroxide. Now that H plus does not like to exist by itself in water. It's going to react with water. There's that double arrow again to form this hydronium. So just likes to show the Lewis structure of how these different substances are going to form. Now, this is actually a term I threw out on the last slide, a dynamic equilibrium, where we have this, what we call a reversible reaction, a reaction that does not go to completion, that forms some products, but not necessarily a lot of products. So we'll say that the rate of the forward reaction equals the rate of the reverse reaction. That's not saying that we have equal amounts of reactants and products. All it's saying is that the rate has equalized. It does not mean we have equal amounts. I'm going to show you a slide that has a picture to help explain this a little bit more. Now, to show a dynamic equilibrium or a reversible reaction, we show that with a double arrow, as I've shown you on the previous slide. A single arrow means that you only make products. It can't go backwards. Double arrow means, well, life's a little more complicated than we like to think sometimes. So here's our example of looking at what's called that dynamic equilibrium. We have two islands. Island A has a bunch of people in it. Island B has a little more solitude. So let's say you're over on Island A and there's just a lot more people. So you decide to swim to go to Island B. Once you've had your fill of that isolation and kind of peace and quiet by yourself, you decide you want to rejoin the group, so you swim back to A. That's a reversible reaction, where you can go back to the reactant state. Now, for this particular example, Island A, what we started with, has a whole lot more people than Island B. So even though the number of swimmers, that's the rate or the flow, is the same. The people on A, the reactants, does not equal the people on B, the products. At the bottom, we've shown the actual little water molecules. And within all of these water molecules, we have one that's broken apart. Everything else is still water. We've had one that broke apart to the hydrogen ion, which then reacts to form hydronium, and we have the hydroxide, but most are still water. As we continue our discussion of pH, we'll see that water mainly wants to stay together. There's just a little bit that breaks apart, and we're going to talk about exactly how much of that actually breaks apart. So how much of water actually does break apart? So it says at dynamic equilibrium for water, that means that the rates have equalized, everything's kind of in a stable place. The concentrations of hydronium and hydroxide are equal to one another. Now we set a temperature of this 25 degrees C. If you change the temperature, it will actually change how much water dissociates. 25 degrees C is like the standard that we like to use. At 25 degrees C, that little square bracket right there, this square bracket means concentration. The concentration of hydronium equals the concentration of hydroxide. Well, that makes sense because one water split into two parts. So we would assume that the two parts would be equal to one another. We're going to look at a case over the next few slides where we've added something so they're not equal to one another again. Anyway, they're equal to one another, and that concentration is 1 times 10 to the negative 7 big M. Okay, do you remember what big M means? Big M is molarity. And if you remember, molarity is moles over volume in liter. So moles looks at the amount of the substance, and then liters that volume. So we have a concentration. Well, what does 10 to the negative 7 mean? Well, that means that we have a really tiny number. So let's see here. It's 1, 2, 3, 4, 5, 6, 7 moles of hydronium or moles of hydroxide in 1 liter. So it's not very much. Very little has actually dissociated. So we've seen that water only partially dissociates. Just a little bit of water dissociates. But what happens when we put an acid in water? Will it dissociate? Will it break apart, or will it ionize, are some terms you might see? Well, how much it breaks apart or ionizes or dissociates depends on if you have a strong acid or a weak acid. So strong does not refer to how dangerous it is. It doesn't refer to how much harm it can do to a person or how much metal it could react with. All strong versus weak deals with is if you put this substance in water, how much does it break apart? How much does it dissociate? So strong versus weak, again, depends on the ionization of an acid to the hydronium. So how much does it break apart? Strong acids will completely dissociate. That means when you put them in water, they're going to break apart. The hydrogen is going to separate from the anion or the negative part of that acid. So we show that in a picture on the bottom, but this is the one on the right. It's letter B. So B, if you look, you can see the little water molecules. Those are the little Mickey Mouse looking things. And then you see a bunch of blue atoms, blue molecules. Those are, but if you notice, it's just the one part. So if we, let's see here, I'm trying to see if it has that term on it. It doesn't. It just says that the molecule is breaking apart. Notice there's no hydrogens attached to those on the right-hand side in figure B. It's just the little blue things. On the left-hand side, figure A, we have weak acids. Weak acids partially dissociate, meaning when you put them in water, most of them are going to stay as an acid. So if you look, most of them are staying as the acid molecule where you have the blue with the white that's attached. But a couple of them have broken apart where you'll see the blue molecule and then you'll see a hydronium someplace else where that H plus has attached itself to a water. This is a reversible reaction, so the parts that break apart can come back together and the acid can then go ahead and break apart. So it goes back and forth. So strong versus weak. Strong completely dissociates. Weak mostly stays together, and a few of them will go ahead and break apart. Now, just a reminder, we said that strong versus weak does not talk about how harmful it is. It also does not talk about how fast it will react to a base. That actually remains the same if it's strong or weak. It's only how it reacts when you place it in water. So weak acids partially dissociate. Now, down on the bottom, we're going to try to show this a couple of different ways. Down here at the bottom, we're trying to show like a bar graph of how much of these different substances we have. On the left, it's before you put it in water. Before you put it in water, we only have acetic acid. Acetic acid is an example of a weak acid. Acetic acid is actually what's in vinegar. So if we look up at the diagram, this is what acetic acid would look like. So we have the blue part, and then the white, which is supposed to represent the hydrogen, is still attached. Now, when we put it in water, part of those acid molecules are going to dissociate. So here's an example of part of it that's dissociated, and here is the hydronium that kind of goes along with it. So the blue and the white separated from one another. The white got attached, or it reacted with a water molecule to form that hydronium. The blue is left by itself. But if you notice, most of the acid molecules are still that blue and white attached to one another. They haven't broken apart. So when you place a weak acid in water, we still mainly have the acid, but a little bit of it breaks apart. We have a little bit of acetate, we have a little bit of hydronium. Those two are equal to one another because, well, they break into two things, but most of it stays together. Now, the strong acids are a completely different story. The strong acids, when you put them in water, they completely break apart. So down on the bottom, we're going to start off with our strong acid. Here it is. And when we put it in water, so there's that dotted line saying, okay, now we're going to put it in water and let's see what happens. If you notice, what happens is that there is no HCl left. So HCl is hydrochloric acid, and it is a known strong acid. It completely ionizes when you put it in water. So we only have chloride ions and hydronium ions in water. If we look at the diagram at the top, you don't see any of the blue with the white attached anymore. They've completely separated. And if we look at how the reaction is written, notice that we have a single arrow right here. On the previous slide, and I forgot to point it out, sorry, the weak acids will always have a double arrow to show that it's reversible. This one only has a single arrow, meaning that it's going to go to completion. We're not going to be able to reverse this reaction.